let's look at the one sample t-test. This is the simplest hypothesis test for a mean. This is a continuation of the video I did about confidence interval for a mean using a one sample t interval. So you should probably watch that first if you haven't watched it. It's the same example. Coffee maker is supposed to deliver 10 ounces of coffee. Same data, random sample of 20 cups, bunch of numbers between 9.5 and 10.2. But now, instead of doing a confidence interval, we're going to see how hypothesis testing works. Again, they're really, it's not like two different kinds of things so much as two different approaches to the same kind of answer. Is it shortchanging me? Here we focus more on the yes or no question. There we focused on, let's figure out pretty much how much coffee I expect it to give me in the long run, and then we'll see if that's significantly less than 10. And we discovered in the other video it really was significantly less than 10. So given that I haven't changed the data, we fully expect to reject this null hypothesis. So the null hypothesis would be that the mean, that's mu, it really is mu, the population mean, the ideal thing that we would get if we had 1 million coffee cups. We looked at the entire life of the coffee maker. The null hypothesis is that that's 10. And we care about just whether it's shortchanging us. So we're going to do a one-tailed test. Okay, so let me make that clear. And that's always based on what we care about. And we could do a test based on, okay, let's discover whether it's different. But we care more about whether it's shortchanging us. So we're looking at whether mu is less than 10. Very similar conditions to what we had before, so I'm not going to go through those in great detail. It's a random sample, that's crucial. We're going to assume that these are really independent of each other. So it's a good, fully independent random sample. We need the 10% condition. Certainly this coffee maker is going to make more than 200 cups in its lifetime. And the same check of the nearly normal condition. And we can't be absolutely sure that this is coming from a normal distribution. And if there's any red flags, we'd want to pay attention to that. But the first thing we do is exactly the same what we did in the confidence interval test. We enter our data into the calculator with stat edit, and we look at the histogram. We could also do maybe a more sophisticated test by looking at the normal probability plot, seeing if it's straight, but maybe we'll do that in a different video. I didn't set that up. With n greater than 15, here the sample size is 20. When it's bigger than 15, we only need it to be vaguely normal. Remember, it doesn't have to be perfect, and certainly that's not something that looks perfectly normal, but it's not horrible. Okay. All right, there's no analogous success-failure condition to check, so we're good. So here's the data. We did 1-bar stats just as before. It's the same screenshot as before. And the crucial things are the sample mean, 9.845, and the fact that that's lower than 10 is our first hint that maybe it is shortchanging us. But then it's all based on how far is that by some sort of standard ruler. And of course the standard ruler we use is the SX, and that's this guy, that's S, 0.1986. Okay, so here's the mechanics of the test. Let's see how that works. Okay, what we do is we just calculate. We look very similar to calculating a z-score. 9.845. That's the sample mean we got. So compare it to the null, the proposal for the mean based on the null hypothesis. Let's see how different they are. It's really basically measuring, is this a statistically significant difference? Now we're going to say, okay, we want to use this as a ruler, but let's be careful. It's 0.1986. That would be the standard deviation if we just took them individually one at a time, or at least that's our guess for what the variability is, the standard deviation if we took them one at a time. But we're not taking them one at a time. We're taking them 20 at a time. That reduces variability by the factor of root n. Okay, so that's really crucial. This is really kind of the appropriate ruler for a sample size of size 20. Okay, so let's go ahead and calculate that, and it gives us a pretty big negative number. Remember, because the t-distribution is pretty darn similar to the normal, your intuition about z-scores is going to translate almost exactly to intuition about t-scores. That's pretty darn low, and we think we're probably going to reject the null. And exactly how low is it? Okay, we want to get a p-value. Okay, that's where we need a little bit of technology. Okay, and what we do is we go to distr, the second on the vars button. We have our usual list, and here's where we use tcdf for the first time. We press that, and we get this screen right up here. And we are looking for a lower tail, because this was a one-tailed on the low side. So we just let, this actually is preset, minus 1e999, an absurdly low number, just basically minus infinity. Then we put in the minus 3.49. We've got to put in our degrees of freedom. Remember, that's n minus 1. And that's because, unfortunately, it's really not so bad. It was a miracle that the normal model, there was just sort of one master normal model we could always use. This just has one other thing we have to make sure that's adjusted to our situation. So this is n minus 1. Click paste. It puts that in. We press enter. We get 0.00122. Okay. So our p-value is p. P is let's see, 0.122%. That is very, very small. Okay. That's a very low p-value. And so what do? We reject the null. Not surprising given what we had seen from the confidence interval stuff. Okay. So this is used in exactly the same way as before. If it's really low, you're going to reject the null. And how low is really low? It depends on what you're doing. Okay. We could have a preset cutoff, an alpha level. Maybe that's 5%, in which case this is much lower. Even if it's 1% or 0.5%, we're still going to reject the null. So even if we really hate type 1 errors, with this kind of data, we're going to reject the null. Okay. So this is interesting that with this mean was different from 10. It wasn't drastically different from 10. But because we've got a halfway decent sample size of 20, not huge, that's enough to actually reduce the variability to a pretty small number. It was 0.2, but then it's reduced by, let's see, let's actually calculate that. Let me show you what that is. That is, oh yeah, we already knew that from the other one. 0.04, okay? And so it was 0.04 ounces is sort of a significant variability based on the data we have. And so the 0.155 ounces is quite significant. We saw that in the confidence interval stuff. Okay, let me show you how the calculator does this all in one fell swoop. If you go to Stat and then Tests, second one here is the t-test. Then you can either do it from the data you've entered in a list or from summary statistics that you enter in. Maybe we'll do a version of that soon. It's talked about in the book. I put in the mu naught. That's the null hypothesis version of the mean. We're comparing it to what we think the mean maybe should be. The list, I put them in an L1 already. There's no frequency data. We're not repeating values using a frequency table. We put in what kind of alternate hypothesis it is. This is very, very like the z-test on the calculator. We can press calculate, in which case we get, we get this screen here. Ooh, that's kind of a cool purple color. And it tells us its conclusion is no mu's less than 10. Reject the null. Here's the t value and here's the p value. And so this is probably what you'd tell somebody the first and the third lines here, and the last line, because you all should report your sample size. They want to say reject the null, very low p-value, so we're pretty definite about it. And by the way, the sample size was 20. That's what we used. And they might want to know the other stuff if they know statistics. Now the picture here, it's really nice to be able to draw the picture. We've got here's the assumption based on the null hypothesis is that if I did this this sample of 20 100 times, I would get a bunch of values in here, values out here, values out here, values out here, values out here, based on the T19 curve, which is pretty similar to a normal model. What did we get? We got 9.845, and that's pretty far into the left-hand tail. It's so far that if we measure it in terms of standard deviations, we look at this t-score, it's minus 3.5, which is pretty darn small, pretty far out in the tail. And then the clincher is the p-value, 0.0012. It's the area under this tail as usual. The probability that if I kind of did this over and over and over again, that I would get a statistic this extreme or more extreme. Now the calculator actually does do that. If you go, instead of when you go to the t-test, if you press draw instead of calculate, it draws you a nice little t-curve. This is the T19 curve, carefully drawn, and it should draw a little line and then shade in the tail. You might wonder, where did it go? Where was the analog of this shaded part I have in my picture by hand? Well, if you think about it, these are units of 1, minus 2, minus 3. That tail is like right way over here. Because this is such a small t-value, it actually doesn't draw a great picture. For example, if the t were minus 1.5, this is what we would see. We'd see that t-curve, and it would shade this in. It would be black, but I use the red pen because it's cooler. Okay, so you can do that as a test, basically to help your understanding. It should confirm the picture that you should be able to draw by hand to make sure you're really doing what you think you're doing with the t-test.